is hacking AWS accounts under the radar. And I'm going to give you a little bit of information before Lior takes over. Many businesses are still struggling to understand the least privilege principle in the cloud. In this talk, Lior is going to present a sophisticated way to stay under the radar while escalating privilege, which could lead to sensitive data exfiltration and sometimes to a total account takeover in the cloud, which is a very, very serious matter. Lior Sonntag is a security researcher at Checkpoint CloudGuard Dome 9. His focus is on researching and analyzing cloud traffic and behaviors, writing signature detection method policies for identifying and securing cloud networks, monitoring and adjusting detections based on their performance, impact, input from customers, and monitoring system for QA teams. So you have an expert today speaking about the things he does best. Lior, take it away.
Thank you very much, Lior. So hello, everybody, and thank you very much for joining my talk about hacking AWS account under the radar. So let's start with a little bit about myself. So as Lior said, I currently work as a security researcher at Checkpoint CloudGuard, and on a daily basis, I'm researching on and analyzing cloud traffics and behaviors. In addition, I'm writing signatures, detection methods, and policies for identifying and securing cloud workloads. And of course, I own a bunch of certificates like the OSCP, GPEN, GXPN, and SEC 545. So in this talk, I'll present a step-by-step demonstration of an AWS attack scenario, including some hacking techniques for defense evasion and staying under the radar. Also, throughout the demonstration, I'll be using some of the most popular AWS services like IAM, Lambda, EC2, and SSM. So let's get right into the business. And let's say that you have successfully compromised a pair of AWS access keys. In this case, these are permanent keys that associate with an AWS user. So what are the steps that we can take in order to advance in our attack? Well, one of the first steps is to discover the compromised username, and this can be achieved by the get call identity. And just like in Linux and Windows systems, we have the whoami command, which will enable us to identify the username. Then its equivalent command in AWS is the STS get call identity. Now, next, we can execute a defense evasion technique by creating temporary credentials from the permanent ones. So in case the permanent credentials will get deleted or disabled by the defenders team, will still be able to have access to the compromised user. And this can be achieved by the STS get session token API call. And by the way, to run those operations, we do not need any permissions. So let's run those two commands and see the results. So in this case, I've entered the compromised credentials to a profile named lowpriv, and I'm running the STS get session token operation. As you can see, we've got the temporary credentials, which will be saved as backup. The second command will be the get caller identity to discover the compromised username. In this case, the compromised username is lowpriv, as we can see on the screen. So what's next? We can try to list the user's policy, the user's permissions by running the following API calls that we see on the screen. But these will be only successful if the compromised user has permissions to run them. So for example, we can try to list all inline and managed policies attached to the user, or we can list all the groups that the user belongs to. And if nothing of this works, then we should consider thinking about brute forcing permissions. So let's try to list the user permissions by running those three IAM API calls and see the results. The first one will be list user policies. And we got access denied. The second one will be list users policies. And once again, we got access denied. Maybe the third one will be successful. And once again, we got access denied. So apparently we are unlucky this time. Now, before getting wild and loud with brute forcing permissions, it is better if we won't give up so fast and try to run specific API calls that are related to some of the common AWS services, like S3, Lambda, EC2, CloudTrail, and so on. So in this demo, let's try to check if we have access to the account's event history by using the CloudTrail service. So once again, I'll use the compromised credentials, and this time I'll run the CloudTrail lookup events API call and see if I have permission to do that. And apparently we do have permission to do that. So we successfully discovered that the compromised user has read-only permission to the CloudTrail logs. So now we can use this permission and try to list all the CloudTrail events history that are related to the low priv user by adding the following filter that we'll see right now on the screen. And we discover that the low priv user has executed the STS assume role API call, as we can see from the event name field. Now, when running this specific API call, we are not required to enter a specific region to the AWS operation. So therefore, we can enumerate the default region being used by the default user from the logs itself. As we can see, marked in white, this is the default region being used by the compromised user low priv, which in this case is US East 1. Now down below in the log, we can see that the role that was assumed by the compromised user. In this case, the role name is Lambda creator, and the role session name is random session. And below it, we can even see the role ARN that was used. So we'll copy this role ARN to assume it later on. Now, before assuming this role ARN, let's check all the CloudTrail events history related to the Lambda creator role, and this can be achieved by changing the attribute value here to the role session name, in this case, random session. And we discover here two events in the log. The first event is that the Lambda creator role has executed the update function configuration API call on the Lambda function named automation update SSM param, as you can see from the resource name. And down below, we can see in the second event that the Lambda creator role has also executed the update function code API call on the same Lambda function, automation update SSM param. So now that we have a general idea about the permissions that the Lambda creator role has, we can assume it by running the STS assume role API call. So we'll give it the role ARN that we copied before. And right now, we'll also give it the role session name. And we got the STS token of the Lambda creator role, which will use it to impersonate it, move laterally, and escalate our privileges. So let's see what we know up until now, according to the Lambda creator role. It can update the configurations of the Lambda function named automation update SSM param, and it can also update the functions code of the same function. Now let's see if we can get the functions code or the functions environment variables by running the Lambda get function API call. So in this case, I'll use the Lambda creator role STS token that we got before, and I'll run the operation Lambda get function API call on the function named automation update SSM param. And sadly, we got once again access denied. So apparently we can't read the functions code or the functions environment variables. So what else can we do? We can try to Google search the Lambda function name and see if any surprising results will appear. So I'll go to Google and type in AWS and the Lambda function name, automation update SSM param. I'll go to the first result here, and we can see that it's an AWS walkthrough about simplify MI patching using automation, AWS Lambda, and parameter store. Now scrolling a little bit down to create an IAM role for AWS Lambda, we can see that the role attached to the Lambda function has managed policies of AWS Lambda execute and Amazon SSM full access. And this is something that we should really care about from the attacker perspective, because this is a very wide permission that we might abuse it later on. Now, scrolling a little bit further to create an AWS Lambda function, then we see on step 4 that AWS uses a Lambda function named automation update SSM param, exactly as in our scenario. And down below, we can even discover the function's name. So we see that it's written in Python, and it also uses the Boto3 library. So you see, users tend to follow AWS walkthroughs to build architectures in their own environment, and they will usually define the resources names exactly as AWS defines them in their examples. So as a rule of thumb, do not name your resources in your account as AWS names them in their walkthroughs, because it is a very common mistake that users do, which might increase the attack surface of the attacker. So let's conclude what we know up until now. Well, first, we know that the Lambda creator role has permissions to update the function's configurations and code. Secondly, we know that the role attached to the Lambda has SSM full access permission. And we also discovered, in addition, that the Lambda function is written in Python and uses the Boto3 library. So the SSM full access is a very wide permission that the attacker would love to abuse it to his advantage, of course. So our next goal here is to move laterally by compromising the function's role credentials, and hopefully we'll be able to escalate our privileges once again. Now, the temporary credentials, or STS token of the function's role, are injected as environment variables inside the Lambda file system. So one easy possible attack vector is to abuse the update function code permission to change the function's code to a malicious one and retrieve all environment variables. And this, for example, can be easily done by reverse shellcode from the Lambda function itself to the attacker machine. But of course, there are some consequences when doing that and changing the code, which might first break the functionality of the function. And secondly, it might alert the defenders that something is wrong with one of the Lambda function. And of course, we would like to avoid it if possible. As an alternative, we can abuse the update configuration permission to inject a malicious Lambda layer to the function and not affecting at all the function's code. And before getting into details about this attack vector, let's talk generally about Lambda layers. First, it allows to include code in your function, but it is stored separately in some kind of a layer. Secondly, all files within a layer are stored in the op directory on the Lambda file system, and we'll soon see why it is important. And last but not least, it can be shared cross-account, which is also a very important attribute which we'll be using later on in the attack vector. Now, when investigating the search path order of Python modules inside the Lambda file system by running the sys.path command, we discover the following result that we see in the bottom screen. So let's say, for example, that we are writing in our Lambda function import Boto3. So this means that once the Lambda function will get invoked, the Python interpreter will first search in the var task directory for the Boto3 library. And if it doesn't find it there, it will continue to the opt Python directory. And once again, if it's not there, it will continue to the var runtime directory, and so on, according to the search path order. Now, the default Boto3 library is located in the var runtime directory. So this means that if we create a Lambda layer, which includes our own version of Boto3 library, then it will be included in the opt Python directory, which means that once the Lambda function will get invoked, it will use our own version of Boto3 library instead of the default one, because it is located in a higher priority. So after understanding this concept, we can now download a Boto3 library and insert the following malicious code into the initiate.python file. So it will start executing immediately. What this malicious code will do, it will send a post request to the following attacker's IP address that we see on the screen on port 4433. and it will include all the function's environment variables. Now, as I mentioned before, the Lambda layer can be shared cross-account. So this means that we can create our malicious Lambda layer, which includes the malicious bolt-of-3 library, inside the attacker's AWS account. So in this scenario, I've created a malicious Lambda layer named backdoor layer. So our next step here is to make this malicious backdoor layer publicly available in the attacker account. And this can be achieved by running the Lambda add layer version permission API call. So we'll do it right now. So right now, our malicious backdoor layer is publicly available, and we can use it to inject it into our Lambda function inside the victim account. So I'll abuse the update function configuration permission and inject our malicious Lambda layer to the Lambda function automation update SM param. And as we can see from the output, the injection was successful. So now all is left to do is set up a netcat listener on port 4433 on the attacker machine and wait for the function to be invoked. Once the Lambda function will get invoked, we'll receive all the function's environment variables, as we can see from the screen. And of course, we can play a little bit with bash scripting here to make it look nicer and more organized. So we'll do it right now. And as we can see, we got the access key ID, the secret access key, and of course, the session token, which together they compose the STS token of the functions role, which once again will use it to impersonate it, move laterally, and escalate our privileges. Now, as a reminder, the functions role has SSM full access permission. So this means that right now we are able to use it and of course to abuse it. So now let's try to list all the history events related to the SSM service using CloudTrail before abusing and going crazy with this permission. So I'll go back to the low-priv user from the beginning that has access to the CloudTrail logs, and I'll try to look up for all CloudTrail events history related to the SSM service inside the whole victim account by adding the following filter that we see in the attribute value. And we quickly discover that the SSM start session API call was used to connect to an EC2 instance that has the following target ID that we see marked in white. So we'll copy this target ID, and now we're able to abuse the SSM full access permission by using the STS token of the functions role and running the SSM start session API call to connect to this EC2 instance. So right now, we were able to log into this EC2 instance using the session manager, and we are authenticated as the SSM user. And of course, we have also root permissions by default. Now, one of the things that an attacker will try to do when he has successfully compromised an EC2 instance is try to query the metadata service inside the instance itself. And the metadata service is located on the internal IP 169.254.169.254. In this case, the attacker wants to find out the role name attached to this EC2 instance. So he discovers that the role name is DynamoDB full access. Now, usually users will give logical names to their roles according to the role's permission. So we can assume that this role has permissions of full access to the DynamoDB service. Now, once the attacker knows the role name attached to the EC2 instance, he can get instantly all the STS token of the functions role by using the following endpoint. And as we can see, we got also the STS token of the DynamoDB full access role. Now, in this case, we'll not use it, and we'll try to list all the DynamoDB tables from within the EC2 instance. So we'll run the DynamoDB list tables, and we discover a table named customers info. So let's scan it and discover all its contents. And we can see some sensitive data about customers, like their first name, their last name, the phone number, email address, and even their last 4-digit credit card number. Really sensitive information about customers. Now, it is just a matter of time until the defenders will realize that their account got compromised by an attacker, and our access as attackers will get lost at some point. So data exfiltration is a very important phase in the attack chain. And of course, there are several ways to do it in AWS. The first way is by using the EC2 Role STS token outside the instance environment. But usually this can be detected easily as suspicious behavior, and we would like to avoid it if possible. The second way is by using DNS tunneling. And this is a very common way to exfiltrate data silently and under the radar. And for example, we can try to use one of the famous tools like DNSCat to do it. And the third way is by using NTP tunneling, which in this specific scenario we'll be using this way. So let's talk about Network Time Protocol, or NTP, in AWS. It is being used frequently to sync the clocks of instances over the network, and it also uses the Amazon TimeSync service on the internal endpoint 169.254.169.123. And in addition, it uses also external time servers. And this is the main reason why we can use it as a data exploitation technique. And of course, it also uses the UDP protocol on port 123. Now, when inspecting the NTP traffic to external time servers from within the EC2 instance, for example, by using the TCP dump tool, as we can see on the screen, then we can discover from the timestamps on the left that very frequent requests are being sent to these external time servers, which once again, it's a very good sign for us that we can use it as a data exploitation technique to exfiltrate data silently and under the radar. So we've reached the final phase of the attack. On the right side, we have the attacker machine setting up a Netcat listener on UDP port 123. And on the left side, we have the compromised EC2 instance from before, which right now we are writing all the contents of the customer's info table into the file data.txt file, as we can see on the screen. And now all is left to do is connect to the attacker machine on UDP port 123 and to his IP address, of course, and transfer all the sensitive data of the data.txt file. So it seems that the data was transferred, so we can validate it. We'll go back to the attacker machine and we can see that all the data about the customers was successfully exfiltrated to the attacker machine. So we've reached the end of this session, and I would like to conclude this whole attack chain process that we've seen, which might seem a little bit complicated at first sight. So we first started with compromised user credentials, and our initial steps was to discover the compromised username. And this was achieved by running the get caller identity API call. We also executed parallelly a defense evasion move by creating temporary credentials from those compromised ones. So in case those compromised credentials will get deleted or disabled, we'll still be able to have access to this compromised user. We then found out that the compromised user had read-only permission to the CloudTrail logs. And of course, we went to this direction and discovered that we can assume the Lambda creator role, and we have also enumerated its ARN and the role session name. In addition, we discovered that the Lambda creator role has permissions to update the code and configurations of the Lambda function named automation update SMParam. So then we use these compromised credentials and we assume the Lambda creator role, which in return gave us the Lambda creator role STS token, which we have used it to impersonate it, move laterally, and escalate our privileges. So from there, by using the STS token, we injected a malicious Lambda layer to the Lambda function. And once it got invoked, we received the functions role STS token, which once again, we used it to impersonate it, escalate our privileges, and move laterally. Now, the functions role STS token had SSM full access permission, which is a very wide one, which we discovered from the AWS walkthrough. So we went back to the CloudTrail logs and searched for all CloudTrail events history related to the SSM service. So from there, we quickly discovered that the SSM start session API call was used to connect to a specific EC2 instance that had a specific target ID. So of course, as attackers, we abuse this information and we have successfully compromised this EC2 instance. From there, once we got inside, it was just a matter of few commands to discover that it had also full access permission to the DynamoDB service. And once again, we abused this permission and discovered a table named customers info, which had some sensitive data about customers. Finally, we used NTP tunneling as a data exfiltration technique to steal all the information from the EC2 instance to the attacker machine silently and under the radar. Thank you very much.
Leo, before you finish, we had one question from our attendee. He's asking if we need a security group that opens port 123 UDP.
Apparently, you have already configured all the outbound traffic by default. It's opened already. When you open a new EC2 instance, the UDP traffic is opened. Actually, all the ports are opened in the outbound traffic. So we can use it to exfiltrate data. And of course, it's bad for the AWS users.
Okay, great. So for our attendees, we have 2 minutes for you to ask another quick question. If there's something you'd like to know, please raise your virtual hand or ask a question in the Q&A panel. Lior is going to finish the presentation in 3 minutes, and we're going to go to the next session. Lior, I love those clouds in the background. I need to get me some clouds. Great session by Lior. Thank you so much. We're getting comments from the audience. It's really enjoyed the session, saying great session, excellent session. Thank you very much. Thank you to our attendees, and we're hoping to see you in the next session in this track.
Okay. Limor, let's put a link to the session that starts in 2 minutes on the chat. If anyone wants to join it, they can do it using the Zoom link that we will post in a minute.
Sure. Okay.